Hello, everyone. Welcome to our final project presentation. We are the Satellite Streaks team. My name is Kilando, and I'm joined by the other two fellows here, Abhilash and Ashley. You can probably see them waving on the Zoom screen. We also have our project leads and data scientists, Dino, Meredith, and Vaughn, who are very integral in helping us accomplish this project. So today we will be discussing the problem, our project and its output, the process behind our summer project, and future work that we intend to impact. So at this point, you're probably wondering, what about satellites impact our ability to perform social good or mitigate social harm? And a lot of people may have this question because they're familiar with satellites as being revolutionary in many arenas, maybe revolutionary in the space race with the release of Sputnik by the Soviet Union, or revolutionary with geostationary satellites that give us GPS navigation. And some people understand satellites to be integral providers of wireless communications and connections such as the internet. But a lot of people aren't really aware that satellites can and do inhibit human beings from being able to access the natural resource that is the sky. And the particular satellites in questions that do this are low Earth orbit satellites. So low Earth orbit satellites are highly reflective of the sun's rays, very similarly to how the Earth's natural satellite, the moon, functions. But unlike the moon, they rapidly orbit the Earth in the span of 30 minutes. And as such, low Earth orbit satellites are visible to the naked eye, posing a threat to nature, culture, and astronomers. In terms of culture, there are global indigenous populations that rely on the night sky as a traditional religious and cultural resource. And the visibility of these low Earth orbit satellites pose a threat to the integrity of this resource, especially since these traditions are passed down orally. In the words of Professor William Sutherland, in terms of nature, low Earth orbit satellites may mislead animals from responding to celestial cues. And in terms of astronomers and astronomy enthusiasts, I want to reemphasize that these low Earth orbit satellites are highly reflective and very fast in their orbits. So in order to demonstrate that, I'm going to show you all a visualization. And as you can see, there are flashes going across the sky here. And those are actually satellites that are visible. And as you can see, they're very bright and very fast. And when telescopes take images, they don't do so instantaneously, but they take a few seconds to actually capture the image. And so those satellites end up appearing as streaks. So to demonstrate what a telescope image would look like, this is an actual telescope image. And this image, as you can see, has a few dots that represent stars and celestial bodies, but more importantly, it also has satellite streaks going across the image. And these satellite streaks makes it very difficult to just explore space for astronomers and for astronomers to also learn more about the celestial bodies that are surrounding us. So we also want to emphasize that the problem isn't just satellites, because satellites aren't inherently bad. As mentioned, they allow us to get great innovations. But the problem is the exponential launch of satellites by commercial aerospace companies. So as you can see in this graph, we have the number of untracked objects and the number of tracked objects in Earth's orbit. And as you can see, there's a general uptick of most of the objects. However, if you look at the blue line at the bottom that says active, this is representative mostly of low Earth orbit satellites. And as you can see, there's an exponential growth in the recent years of the amount of satellites that are being released into orbit. So if I have not convinced you of the gravity of the situation yet, I'm going to show you a simulation. And each of these pictures are simulations of the Earth. And surrounding the Earth are dots. And each dot represents a satellite. And the color of each dot represents the company that has launched or intends to launch the satellite in question. So in 2019, we see there are some, but not an overwhelming amount of satellites in the Earth's orbit. But in 2021, we see that there is an exponential growth. And this is the true amount just last year. And in 2023, although 2023 has not happened yet, these are estimations based on aerospace companies filing with institutions about their intentions to launch satellites. We see that there is a striking amount. And in 2025, the exponential growth is so visible that the Earth is covered with a cloud of satellites. And we also want to discuss the fact that There are no regulations on the brightness or numbers of satellites that are launched by these companies. So to reiterate the problem, there are a large number of low Earth orbit satellites, and as such, this creates streaks in astronomical images, making astronomy research for both astronomers and astronomy enthusiasts very difficult. So hopefully I've convinced you that the satellite streaks are definitely a problem. So let's examine how our team's project attempts to address this problem.
Great, thanks, Kilando. So with that overview of the problem, we believe that one of the first steps towards tackling this issue is sort of quantifying the impact of this problem, such as quantifying the properties of the satellites, quantifying to what extent do they damage the astronomical images. And that is specifically the motivation of our summer project, which is to detect and quantify satellite streaks in astronomical images. So in terms of the current work done on this topic, we have astronomers tracking individual constellations of satellites such as Starlink, and we have telescopes that regularly capture images containing satellite streaks. And what this data leads to is analysis of this kind where certain properties of the satellite streaks are quantified. However, one of the drawbacks is that these are mostly like bespoke, manually done analysis that cater to the specificities of that particular image or that particular telescope. And we want to take this forward by scaling up this process and making it more generalizable. So starting with the current body of work, we want to leverage computer vision algorithms and create a generalizable tool that can take in a wide variety of images containing satellite streaks from a range of telescopes on Earth and obtain basic information on these streaks properties. And as a next step, like there are many use cases for this basic information. One of them, for example, is that we know a lot of satellite operators are currently working on mitigation strategies to reduce the brightness of their satellites. And this tool could provide at-scale information to these operators on whether their mitigation strategies is working or not. So with that overview of like our goal, I want to present you our output from this summer project, which is a Python library called SatMetrics that can detect and quantify satellite streaks in astronomical images. We use an open data repository for astronomical images affected by satellites called Trailblazer to build this tool. So at a high and simple level, the SatMetrics library can take in like a wide range of images containing satellite streaks. And if like those images have a streak, then detect that streak and output basic information about the streak that can lead to further analysis downstream. And all of this is towards the hope that like generating more information and more analyzable information on this topic can draw more attention towards this problem and probably support like possible policy interventions towards this issue. So now I'm going to spend some time talking about our process of how we built this library. So at a high level, there are three basic steps that we follow to create this. The first one is detecting straight lines in images. The second one is validating those straight lines to differentiate them from noise. And once validated, like we want to measure the properties of those streaks. So I'm going to talk more about the detecting lines part. To begin with, like detecting lines or straight lines in an image basically means like finding which pixels in that image contain that straight line so that we can study the properties of those specific pixels. So we use a widely used straight line detection algorithm called Hopf transformation to build this tool. So over here in this image, it's an example image. It's binary. So all the dots that you're seeing are like the only non-zero pixels in this image. And essentially how Hopf transformation works is it counts the number of non-zero pixels on every possible straight line in an image, a possible straight line being a collection of at least like 2 points. And more the number of non-zero pixels in a straight line, the higher chances of the algorithm voting it as a possible line. So as you can imagine, with the existence of noise in an image, the accuracy of this algorithm goes down. So along with returning what actually is the streak or the straight line, it can return a bunch of like false lines that essentially just represent noise. And that is the key challenge that we deal with in this part of the process. So on the screen, you can see like multiple real astronomical images containing like a wide amount of noise and differing like noise to like, pixel noise to streak brightness intensity. And consistently removing noise in like these wide range of images so that we can detect lines in them is the biggest challenge for this step. So we use various standard image processing techniques to like deal with this problem. And I'm not going to go deep into like each of these methods, but I'm going to motivate all of these by walking through an example. So on the left, we have like a original astronomical image with like containing multiple streaks and a lot of noise in the background. As a starting step, we try to estimate the background in this image so that we can remove that from the raw image. So on the right, you see like the image where the background of the original image has been estimated and removed. And you can see like some reduction in the amount of noise. Once we do that, like we apply binary thresholding and adaptive blurring of the image to progressively reduce noise. And one of our key assumptions around these steps is we expect the satellite streak to be like on the brighter end of objects in that image. And finally, after applying edge detection, we apply the Hopf transformation algorithm. So you can see the image on the right, where we have like the straight lines being detected and returned by the algorithm. One of the challenges that we face that is again related to noise is sometimes when there's like a lot of noise surrounding like a satellite streak, we can have like multiple straight lines returned that essentially represent the same single streak, as you can see in this image. And to tackle this problem, we use like a clustering approach that I'm going to like demonstrate through like a different example. So on the left, you have like another example of an astronomical image containing a streak that does not go through the entire image, and you have a lot of noise surrounding that streak. And on the right, you can see what our algorithm returns as straight lines. So you can see that the actual streak line is returned, as well as a bunch of other lines are returned, which essentially represent noise. So we try to cluster these into groups, where each cluster essentially represents like either a single streak or a collection of noise. So on the left, we have the straight lines returned, and on the right, we have like successfully clustered it where like the actual streak is contained in a separate cluster and we have noise in a bunch of other clusters. And the reason we do this is because we have validation algorithms downstream that can separate like noise from straight lines, but we don't want to waste computation by running that algorithm on every single detected line. So when we divide it into clusters, we can apply that algorithm at a cluster noise, cluster level, and like perform our validation. So I'm going to pass it back to Kilando to like speak more on this part.
Thanks, Abhilash. After we found clusters of Hopf lines that may represent a streak, as Abhilash said, we want to validate that what we've actually found is a streak. So to do so, we take the median pixel values of each row of an image and analyze the profile of that data. We look for key elements such as, is the fit of the profile approximately Gaussian? And if so, does that profile have an amplitude or a width that is characteristic of what we think a streak would look like? But before we can perform validation metrics, we have to rotate the streak. Our goal is to rotate all of the streaks in an image such that each streak is horizontal, and we crop those streaks so that they're the only streaks in the rotated image. So when Hopf lines finds the streaks, they find them in polar coordinates. So we start by finding two Cartesian coordinates of the line. We choose 2 points, the point at which the line enters the image and the point at which the line exits the image. We use those 2 points to calculate a slope, and then we use some basic trigonometry to calculate the angle of rotation. But when we rotate the angle, when we rotate the line about the angle and the image, it only rotates at the center point of the image. And so it's very difficult to find where the rotated line actually is. So to mitigate this problem, we basically set an anchor point, which we decided would be the midpoint of the line. So when we crop the image, we can easily locate where the rotated image is and crop it so that it only contains the streak. In cases when there are more than one line in the cluster, we take the mean, entrance, and exit Cartesian coordinates and perform the same computations.
So just to reiterate, rotating streaks allows us to do efficient streak analysis. So now that we've figured out how to rotate the streaks, we can now take an image and plot its pixel intensity values. The point of plotting pixel intensities is to tell us what and where the brightest object is located in our image. We take the median of the pixels because since a streak is consisted of clustered and extended pixel intensities, it offsets any outliers and gives us a more obvious peak. So in the top image, we have a bright star with some background noise. We see that the pixel intensity plot on the right side generates very narrow peaks, whereas on the bottom, the peak is more obvious in that it represents the streak in the image. Because this plot looks approximately Gaussian, we use a Gaussian as our model to fit a line through it and determine whether or not we measured a streak. So here we give an example of what a bad fit looks like. In the image above, we see that there's no streak, but rather just some bright stars and noise. Because there's no streak, the plot of this image contains narrow peaks and doesn't look approximately Gaussian. So when we try to fit a line through it, it doesn't converge and due to not passing our validation. So we would throw this plot away because this tells us that we're not measuring a streak, but rather some background noise, which based on the image we see here is true. So this means that this data is not useful to us and we would throw this one away and won't continue property measurement on this image since there's no streak. So what happens when we do validate a line within an image? The next step is to measure the properties and extract the quantification metrics of the streak. So here we have an image of the streak and its pixel intensity plot next to it. The red line on the right side of the plot is our fitting line, and visually we can quickly tell we have a good fit since the red fitting line is very close to the blue real data line. But what happened here statistically is that the normalized root mean square deviation, distance from the middle, and full width half maximum pass thresholds that pass validation. And since it validated and converged, we can confirm that we've measured a streak. So in this case, we keep this data and extract all the quantification metrics that Kilando mentioned earlier. Another great benefit of fitting a line through our data is that we're able to use these metrics to help further the rotation angle algorithm. Sometimes when we would rotate the streaks using basic trigonometry, the streak would not come out completely horizontal, which would make the property analysis less precise. To straighten the streak, we rotate the angle on the Hopf transform line with new angle calculations that are pretty close to the original calculated angle. Once we have our new angle calculations, we have to test them to see which one is the most accurate one that straightens the line. So here we see only 6 rotated iterations of one image. We apply the fitting function on them and assume an image with the smaller normalized root mean square deviation is more representative of a straighter streak to help us make the rotation more accurate. Here on the we see on the last image on the bottom right side has the lowest normalized root mean square deviation, and its line is fitted very closely to the real data. Because we see this, this means that the angle calculation that we have for this image or graph is going to be the best one for our rotation algorithm and allows us to measure our streak properties with more accuracy. So with all the work done within line detection, validating lines, and property measurement, we came down to our StatMetrics Python library that successfully outputs quantified streak properties from the images. StatMetrics is a public Python library that is meant to be used by anyone interested in analyzing satellite streaks and images, whether that's an astronomer doing research on satellites or enthusiasts who took pictures of the sky, noticed streaks in their images, and want more quantifiable information on the streaks. StatMetrics does not end here, though. There's still further developments that are important for our package. But before we dive into that, here's a quick recap of satellite streaks and astronomical images. The initial problem is that the industrialization of space makes the sky brighter, which causes environmental concerns, disrupts cultural traditions for communities, and produces satellite streaks and astronomical images, which makes studying the stars, galaxies, and our universe more difficult for astronomers. In order to study how streaks affect astronomy, nature, and cultures that rely on the sky, we first need a standardized set of measurements and analyses tools to characterize these satellite streaks, which is what our StatMetrics Python library is, a tool that outputs standardized sets of measurements in order to further analyses of streaks and images. So the next steps are a working solution. It's important to measure the brightness of our streaks, which are characterized through magnitudes, which are astronomical brightness units that astronomers rely on. We hope to use the measured pixel intensities to convert into magnitudes so astronomers have more additional useful information of the streaks. This will also help with evaluating if the streaks would be visible to the naked eye. So far, we've only tested our data on a variety of streaked images from the Trailblazer repository, but we want to continue testing this by creating test datasets and continue measuring the precision of the metrics. And finally, our long-term goal is to integrate our Python library to the Trailblazer repository, so when someone uploads their streaked images, our library can generate quantified streak data. Overall, we're very excited that our Python library could aid astronomers or enthusiasts in the research of satellite streaks so that they can come down to more feasible solutions at addressing the overarching problem of satellites. Thank you so much for your attention. We will leave the summary slide up for your reference. We're open to taking any questions.